Hi, this is Ms. Fitzmaurice, and this video is an explanation of the first banked curve problem. Alright, so this problem says the banking at the famous Daytona Superspeedway is 31 degrees with the horizontal. The pavement provides a coefficient of static friction between normal tires of 0.850. Okay, so we know that we have a banked curve, and we know that mu s is equal to 0.850. Okay, we know that a normal car, and part A and B are about this normal car, have a speed of, or have a mass of about 800 kilograms. Okay, so in part A, we want to know, can a passenger car stop and remain motionless? So to figure this out, we need to know, is FF greater or less than mu s times Fn? Okay, mu s Fn, whatever this number is, that's the biggest friction can be before the car starts to slide down. Okay, so let's take a minute and draw our force body diagram. In part A, our car is stopped, so this is essentially a hill problem. We have Fg going down. At this point, friction is holding the car up. F friction is going up the hill, and Fn is straight out the hill at 90 degrees. Okay, because this is a hill problem, we are going to make our x and y axes as follows, x and y. And so we have to break Fg up into x and y. So again, we need to solve for Ff and then check, is it greater or less than mu s times Fn? Writing out our x equation, sigma fx equals m ax, we assume ax is equal to 0. Okay, and then we have right minus left, so it's fgx to the right minus ff equals 0. Fgx is mg sine theta, so sine 31 in this case, and ff will be just ff. We don't know that it's mu s Fn. Okay. So we have mg sine theta minus ff equals 0, and ff is equal to mg sine 31. Now, if we have 800 for m and 10 for g, sine of 31 is about 0.87, and so you end up with a number that is about 4,042 newtons. Okay, now we want to compare that number to mu s times Fn. To do this, we have to find Fn using our y information. So we have sigma Fy equals may. We have Fn minus Fgy equals 0. Fn equals Fgy, and Fn is equal to mg times cosine of theta. Okay, we can now calculate mu Fn. We know that mu is 0.85, so we have 0.85 times 800 times 10, and cosine of 31 is about 0.87. Sorry, this sign was about 1/2. I botched that, but this number is still correct. And when we calculate that, we should get about 57 17 newtons. Okay, so what that means is that our actual friction force is smaller than mu Fn, the maximum friction force, so the car can remain at rest. Okay, in part B, it wants to know what is the maximum speed a passenger car can safely achieve going around this curve without sliding up the ramp. Okay, so if we're worried about the car sliding up the ramp, friction is actually going to be in the opposite way because this car is moving around in a circle. Okay, remember that for problems in which we have a banked curve, so the last problem was more like a hill problem because the car was stationary. Here we have a banked curve problem that we want to use the normal x and y axes, like the ones I've just drawn in green. Okay, so we also know that we want to know the speed. To find out the speed, we can use our x direction. Sigma fx equals max. Since this thing is going around in a circle, ax is actually centripetal acceleration, ac, which is equal to vt squared divided by r. Okay, now our x direction we have fnx plus ffx is equal to max, which is mvt squared divided by r. And if this angle is 31 degrees, we can see that ffx will be 31 times, ff times cosine 31 and that this angle is also 31 degrees, so fnx will be fn times sine 31. Okay, however, we still don't have a number for Fn. Since this is the maximum possible speed, we can use the maximum possible friction. Ff is equal to mu s times Fn. Okay, so I'm going to sub that in for Fn, for Ff, and we will get Fn sine 31 plus mu Fn cosine 31 is equal to m vt squared divided by r. Now we have to look at the y direction. So we have sigma fy equals m ay. Okay, we have up minus down, so fn times cosine 31 minus fg, so that's minus mg, minus mu fn, and that's going to be sine 31 because this is the y part of ff. Okay, so all of this, if you're wondering where I got it, is ffy is equal to 0. Okay, now I'm going to separate, I'm going to bring the mg to the other side, and I'm going to factor out fn. So I have fn cosine 31 minus mu sine 31 equals mg. Okay, and I have enough information now to solve for Fn. I know the mass is 800, G is 10. I'm going to hold off for a second because I bet that my masses will cancel out. And so I'm just going to solve for this algebraically. And I know that Fn is equal to mg divided by cosine 31 minus mu sine 31. Okay. Now I'm going to take what I found for Fn. So that's mg cosine 31 minus mu sine 31. And I am going to plug that in up here everywhere I have Fn. Okay. First, actually, I'm going to factor out my Fn. So I have Fn times sine 31 plus mu cosine 31 is equal to mvt squared over r. For Fn, I'm going to put in my mg divided by cosine 31 minus mu sine 31. Again, I'm just substituting this expression in for Fn times sine 31 plus mu cosine 31 equals mvt squared over r. Now you can see that I can get rid of my m's, and in order to solve for vt, I need to multiply both sides by r. So multiply by r, and I'm just going to put an r up here. And my very next line, I'm going to write on the next page, but you can see that vt will be the square root of rg times all of this sine 31 plus mu cosine 31 divided by cosine 31 minus mu sine 31. Okay, and at this point we can just plug in numbers and solve for v. So we have vt is equal to r, and it tells us the radius is 100 meters. So 100 times g, which we can say is 10. And then we can plug in sine 31 plus 0.85 cosine 31 divided by cosine 31 minus 0.85 sine 31, and all of this you can stick into your calculator, and when you 54.5 meters per second. Alright, in part C, it's basically the same situation, except we're trying to find mu. Okay, we also don't know mass, but that should be fine. Okay, so instead of redoing everything, we can look back at our force body diagram for part B. And we can also look back at our equations. Okay, so we can look back and we know that Fn sine 31 plus mu Fn cosine 31 is equal to mvt squared over r. So I'm going to take this equation. Okay, and I also know over here Fn cosine 31 minus mu sine 31 equals mg. So I'm going to take the two blue boxed equations and work from those. Actually, I'm sorry, on second thought, I'm going to work from this equation right here. Vt equals rg sine 31, etc., etc., except I'm going to square it and bring everything outside of the square root. Okay, so this is where I'm going to start. I want to isolate mu, so I need to get mu out of the denominator. I'm going to cross multiply, and really I'm multiplying both sides by this that I just circled. Okay, and when I do that, I will get VT squared cosine 31 minus mu sine 31 equals RG, and that RG is going to distribute sine 31 plus RG mu cosine 31. Okay, so this VT squared is also going to distribute. I have VT squared cosine 31 minus VT squared mu sine 31. Okay, and I'm just going to bring down what I had on the other side. At the end of the day, remember that I'm trying to get mu. Okay, so I want to rearrange this so that I have all my mu's on one side. Okay, so what I'm going to do is I'm going to add VT squared mu sine 31 to one side, so I'm going to bring this term over here with addition, and I'm going to take away the RG sine 31 with subtraction. Okay, so when I do that, I have VT squared cosine 31 minus RG sine 31 equals, and I understand this is a mess of algebra, VT squared mu sine 31 plus RG mu cosine 31. I'm going to factor out the mu. Okay, so when I do that, I get mu times VT squared sine 31 plus RG cosine 31. Okay, and on this other side, I have VT squared cos 31 minus RG sine 31. My last step is to divide both sides by this term so that I get mu by itself, and I have mu equals VT squared sine 31 plus RG cosine 31. I made a mistake. It's VT squared cos 31, because this is what was on top. What is on the left side will become our numerator, minus RG sine 31 divided by VT squared sine 31 minus plus RG cosine 31. I'm just taking this and dividing, so that becomes our denominator. Okay, our very, very last step is to plug in our numbers. And when we do that, I'm not going to write all the numbers out, we end up with 0.64. And that is a reasonable coefficient of friction for rubber if you think back to the shoe lab. So that's how you know that you have a reasonable number. Okay, so I understand that this is kind of a mess of algebra and you're swimming in algebra right now. Hopefully from this video, the main thing that I want you to get, besides the mess of algebra, is that if you have a banked curve, acceleration is towards the center of our circle. Okay, so that's towards the direction I'm drawing this orange arrow. Okay, and that fnx plus ffx is equal to max, and that our ax is vt squared over r. Okay, that's the important physics part. The rest of it is just algebra. A lot of clunky algebra, but just algebra. See you guys tomorrow.